Hi everyone. So section 3.5, the quasi-binomial model. So we would like to generalize the estimation method in 3.4. In 3.4, that we allow the one more parameter for binomial distribution. So expectation of y, so y is binomial. So originally we assume that y is binomial. NP. So expectation of y is equal to NP, and the variance of y is equal to n times p minus 1 minus p. But we allow that we have one more parameter, sigma square, to explain the over dispersion of the variance. So we deviate from this assumption and we allow this sigma square, and we would like to generalize it. And the idea is to use the based on a specific distribution of y. So even when the specific distribution may not be true. So for example, the often, that we have to assume, always we have to assume the likelihood function to do maximum likelihood estimation, but we don't know, for example, if observations are normal. For example, the stock price, the asset return of the stock, one stock is approximately normal, but we don't really know if it's really normal or not. Idea is that still that we use the normal distribution, and still the estimated parameters are consistent and asymptotically efficient. So if the distribution is not correct, then the such an MLE may not be the best choice because we misspecifies the distribution. But still that we have good or asymptotic efficiency. So consistency means that finally the parameter estimates converges to the true parameter. And asymptotically efficient means that if we have large sample size, estimator is as good as the true maximum likelihood estimator. Yeah, so the one example, for example, the one example is the law of large numbers. Okay. So for example, suppose X follows maybe Laplace distribution with mean mu, and maybe sigma, maybe the variance b or something. So that f of x is the 1 over 2b exponential negative the x minus mu absolute value over b. So this distribution actually, and think about that we estimate the parameter mu. So to estimate parameter mu, always the x bar is consistent for mu. So as sample size gets larger, anyway, x bar approaches to mu. But x bar is actually the maximum likelihood estimator for normal distribution, right? So we they minimize the distance between observations x1 to xn and mu. So x bar is basically ML Gaussian normal distribution, okay? But finally, it goes to mu. So anyway, we can estimate the mu. So this is, a kind of primitive example of the quasi likelihood estimation. So even if the x bar is not MLE for this specific distribution, actually MLE for Laplace distribution is the median of x. So it's like it converges to mu anyway. And the second example is the Gauss-Malkov theorem. In Gauss-Malkov theorem, beta hat estimated parameter converges to beta, and also the variance of beta hat is smallest among all linear estimator of beta. Okay, so that means, okay, so we don't really know the distribution of y or distribution of error. If we assume the normal distribution, still the beta hat is consistent, and also the variance has some good property. At least among linear estimators, it has smallest variance. So we generalize this idea. So we use the MLE based on a specific distribution, even if we don't know if it's true or not. Yeah, so in the next video, we have more detailed discussion of quasi-binomial, quasi-maximum likelihood method.